the work problems in front of the class Monday, okay? And you will get credit for that. So please be ready for that, okay? May even do a little bit today. All right, so we were discussing kinetic and static friction Monday, and here we see graphically, and if we do the friction lab, which we probably will, I don't know if we're going to do the air resistance lab or not, because I get mixed results out of that sometimes. But I would really like to, so we'll think about it. But I'm for sure going to do the friction lab because it always turns out really well. But when you're graphing an object, or if you're pulling on an object with high static friction, and typically how we simulate that is just to put a large mass on, say, a wooden block, okay? As you pull, you will get a straight line. You should, because remember we said that static friction is equal to or less than mu mg, right? So as we're pulling on the object, until we reach the maximum static friction, which is right there, we should get a straight line. These should be equal to each other, or should I say directly proportional, okay? Because why? Because of that right there, acceleration. You know that force and acceleration are directly proportional. Hopefully you saw that in the lab Monday. But once we break or exceed static friction, then you'll get this real sharp peak downward, and then you should get something like you see here, okay? And it's a really good experiment, and it shows us shows us the relationship between static and kinetic. And notice that kinetic, mu of k, is always less than, or mu of k, f of s and f of k. F of k is always less than f of s, okay? Needless to say, mu of s, or mu of k, is always less than mu of s, okay? And notice it's fairly constant. Notice it's fairly constant, okay? So here we see increasing force, all right? But here we see constant force, all right? Okay, and if you have a constant force, doesn't mean it's not accelerating, it's just constant, okay? It means that the acceleration and the acceleration is not changing, right? Okay. And that's what it looks like if you do them together, and it's really the best way to do it. Best way to do it. And we'll do that one, and mostly what we'll do is have a force sensor, a wooden block, puts 500 grams or so on it, pull, and then boom, it'll break free. And you should get really good results, okay? Okay, now, all right, and I wanted to show you this slide. I think this is in your book. It should be. Yeah, well, shoot, it's not. It may be in the back. I bet it's in the appendix. No, there it is. It's on page 143. If you look on page 143, you see this very same table, and I want to, again, get you to understand the difference in static and kinetic friction. Notice that on steel, if it's static, it's fairly high. Once it begins to move, it drops down some. Not a huge drop, but it is a drop. Aluminum on steel, copper on steel, almost half. Brass on steel, not much of a change. Notice zinc on cast iron, huge drop. Huge drop. Okay? Copper on cast iron, huge drop. Okay? Cast iron is a rough metal. When you pour cast iron, it doesn't finish smooth. Whereas copper, when you pour hot copper, molten copper, it typically finishes pretty smooth. Okay? Fairly smooth. Okay? Glass on glass, about a little more than half. Copper on glass, not much. Notice Teflon on Teflon. Look at there. That's why it's called non-stick. It will not stick. Okay? That's why it's called non-stick. Duh, right? Teflon on steel. Same thing. You know how Teflon was discovered, don't you? It was an accident. Like many of our major discoveries, was it penicillin? That Fleming knocked his petri dishes over into the strep, into the penicillium, or vice versa, and he didn't really realize it had happened until he came back the next day and analyzed it, and he saw everywhere it touched it, killed it. Real interesting story. You know that story about how Alexander Fleming came to who he was, don't you? Alexander Fleming grew up a very poor, just basically a pauper, okay, very poor, in England. And one day he was walking down the road and he heard somebody screaming for help. And there was a pond nearby, so he ran over there to the pond, and there was a kid drowning in the pond. About his age, maybe a little younger. And so he dives in, the kid couldn't swim, saves the kid from drowning, probably 8 or 10 years old, something like that. And so the kid he saved, his daddy was filthy rich. And so this is God's truth, this really happened. And so I hope you don't mind me telling this. I want you to give you a little more bang for your buck, okay? You need to know this stuff, though. He met with Alexander's father and says, I want to do something for you. I want to give you a lot of money. He said, no. He said, my son did what anybody ought to have done. He said, anybody ought to do that. You don't need to receive money for that. And he said, well, will you let me send him to the best schools in England? And he thought a minute, and he said, yeah, I'll let you do that, because at least my boy can grow up and get out of poverty, Well, of course, he eventually went to Oxford. And, of course, we know that he became who he was, Alexander Fleming. He discovered penicillin. And, of course, penicillin was discovered right around the start of World War II, 38, 39, somewhere right in there, early 40. And, of course, one of the big killers of people, especially in combat, especially if they've been wounded. Stonewall Jackson died from pneumonia. Many of your wounded vets before penicillin would die from pneumonia because they didn't know how to treat the patient a lot of times to keep them from getting pneumonia. Well, you know who the person was that he saved from the pond? Nobody knows this. Oh, you need to know this. It was Winston Churchill. How big of a save was that? Winston Churchill. And later on in World War II, I think it was 43, 44, Winston Churchill contracted pneumonia. And thanks to penicillin, and it was very heavily guarded too. They didn't want any of the Axis powers getting hold of it. They wanted all their people to die because that way they wouldn't have to fight them again. You know what I mean? I know that sounds kind of crude, but come on, y'all, war's war. You don't go out there and throw pansies at each other, and ring around a posy, pocket full of posy. That's just war, and that's horrible, but it is, okay? So he saved Winston Churchill twice, when he was a kid and when he was an old man. How about that? So, doing the right thing many times can pay off. I was going to tell you now about Teflon. Dr. Wallace Carruthers at DuPont was brilliant organic chemist, and DuPont gave his team of researchers $10 million in the 1930s, and bless God, in the 1930s, that was a lot of money, especially during the Great Depression. It's a lot now, but it is like mega lot, okay? And, of course, DuPont had it. Come on, y'all, how much are they worth, It was like, pocket change, go buy a Coke, for them. And it took them about 10 years, but they finally discovered nylon right around the beginning of World War II, okay? So it took them about 10 years. Well, later on, about in 42, 43, some of his chemists, including himself, were working on Teflon, or trying to do more experimentation and research with nylon. And they thought, well, hey, how will it react with fluorine? Well, they had their apparatus and everything set up, and they said, okay, let's start the experiment. Well, they started the experiment, and nothing happened. And they thought, well, that's crazy. We know we got to get something. And so they got to checking everything out and come to find out there wasn't any fluorine left in the bottle. And they thought, well, we know the bottle had fluorine gas in it, so something's going on. Well, let's just saw the bottle in half and see what's going on. So it's almost like the reaction's already taken place. And it had. What they didn't know is their valve wasn't completely sealed. There's a leak or something, and when they connected it to the apparatus with the nylon in it, it reacted up in the bottle. And they sawed it in half, and the stuff that was in the bottle was Teflon. What we know is tetrafluoroethylene, is that right? Tetrafluoroethylene, is that right? Teflon. So it was kind of an accidental discovery, okay? So it's pretty neat how science plays out sometimes. These great discoveries we have kind of play out, right? You know, the same kind of the discovery, same way the discovery for smallpox. He took cowpox and killed it, and then he thought, well, I'm going to do this, and injected it into people, and when they come in contact with it, they didn't get smallpox. So, and of course, he knew, I can't remember who was the one that did that vaccination. Anyway, he noticed that the milkmaid girls never would contract smallpox because they were always milking the cows. And he went from there, and they thought, well, let's try this, and it worked, okay? All right. It's been eradicated now, other than the CDC. They have smallpox on. That kind of scares you, doesn't it? It's still on the earth. It's just not out there, we hope. Okay? All right, so much for our little sidetrack there and a little history of science and of Teflon and of penicillin, okay? Now you know. I can't believe nobody's ever told you all that. Well, okay. I guess it was meant for me to tell you. Okay. All right. So you see the difference. Notice there's a huge difference on most of them except for Teflon. So again, kinetic friction is less than static friction, or else it wouldn't move. Now what about terminal resistance? Now if you look on page 148 and 149, and I'm not going to go through all this, you can look at it. 148 and 149, we see the derivation of terminal resistance. Now the next slide, well, I'll just save that for the next slide, but the relationship between an object falling and accelerating through the air and its speed is an exponential relationship, meaning what? Well, notice we've got one equation here. Well, they list this equation here, and that can be listed as force, okay, is equal to dv squared. There's actually two equations. As an object is falling through the air, before it reaches its terminal speed, it is still accelerating. And of course, that acceleration is g, right? But once it reaches equilibrium, remember what that means. That means that the velocity or speed is constant, okay? So once it becomes constant, then notice that this relationship right here is equal to mg, okay? Now, you say, well, how do we know what the terminal velocity of an object will be? Is it the same for all objects? No. For objects, and again, if you want to see all the breakdown, the derivation, you can look on page 149. For objects that are, let's just say small objects that have a low mass, small objects, the relationship is this right here. F is equal to kV, okay? And K is a proportionality constant. Proportionality constant that is basically determined by several things, a couple of different things. We could just say the properties of the material. Okay? All right. In other words, is it flat? Is it round? Is it square? Or if it's a fluid, okay, it could be a fluid. Is it very viscous? Is it non-viscous? For example, we do the demonstration with the paper. I don't want to use those, but you've all seen me demonstrate the paper demonstration where you take, and you've all seen this, I'm sure, where you take two pieces. You can take a piece of paper, okay, and a flat piece of paper and a flat piece of paper. We know they're going to float. But why is it that we do this right here? Now, they're the same mass, and we do this demonstration. You've all seen this demonstrated before. And the paper hits first, okay? Air resistance, yeah. And why is there so much air resistance? Well, because of the shape, okay? So that K, that proportionality constant, is the shape. It does involve the mass a little bit, okay, what we call a drag constant, okay? All right? And so for small objects, notice that the relationship is directly proportional to the velocity, but notice it's just velocity. In other words, if the force the velocity is 2, and let's just say that's 1, then the force is 2. If the velocity is 4, then the force is 4, and so on, okay? However, for large objects, now I'm going to delete this, okay? For large objects, more massive objects, okay, the relationship, and this is on page 148, is F is equal to dV squared. And of course, again, D is what we call our drag coefficient. Okay, our drag coefficient. And again, what is that drag coefficient? Depends on the material, depends on the size of the material, okay? Atmospheric conditions come into play here. Needless to say, I mean, this is commonsensical. If you have very dense air, very humid air, you would have more drag, wouldn't you? Because of the water vapor. If you have very, very dry air, then you're not going to have as much drag, right? Why do you think they test all these rockets and airplanes and stuff out in the desert? Okay? All right? They test it out there. For one, it's always dry, and there's very little weather they have to deal with other than the heat. And two, it's, you have less drag. Okay? And that's why you see most all of your major airplane testing is going to happen out at, was it Andrews Air Force Base? More than likely. If I'm not mistaken, that's where the speed of sound, Chuck Yeager broke the speed of sound in his, what was it, X-1? Yeah. And there was another guy, too, that they kind of competed with each other. Was it Scott Westerfield? Was that his name? They kind of swapped back and forth. He would break it, and then Chuck would go back and go faster, and he would break it, and they kind of became a duo. It was just kind of, well, they kind of got to where they were the top dogs in test pilots. Because they were constantly trying to break each other's record. But when you're talking about guts, because they got in those were experimental planes they'd get in. Sometimes some of the people before them that blew up and they died. I mean, it was like they literally lay in their life. Oh yeah, the X-1 wasn't nothing but like a rocket with a seat on it. That's about what it was. Yeah. So I mean, when Chuck climbed into that thing, he didn't know what was going to happen. Because you got to realize we didn't have the engineering skills and the understanding of airflow over a airframe like we do today. And again, that what we know came out of a lot of that testing, because they realized they had to build the plane a lot stronger, because at 800 miles an hour you're putting a lot of pressure on the parts, on the wings. Okay, you're not going to take an old B-17 and fly 1,000 miles an hour. It will fly all to pieces. Okay? You understand what I'm saying? B-52s, those things it's amazing. They still use them. It's amazing to me how well built those B-52 bombers are. If I'm not mistaken, they're still flying today. Been here since the 50s. It really is. And I don't know what their speed is. It's on up there. It's not like the spy plane, but the XR, was it? Yeah, 71. Yeah, that thing flies at probably Mach 5. Yeah, it gets so fast that the fuselage gets hot. It heats up at top speed. That's crazy. That's fast. All right. Okay. All right, so that D there's drag coefficient. Again, you have a table for that. That's a constant, okay? All right, and so that's the relationship really of fluid. When we say fluid resistance, most of the time it is air. But what about moving through water? Okay, well that's your drag, okay? And what about other liquids and other liquids? What about, say, oil in gasoline or oil in water? Which you're probably not going to have many situations where you would have those two together unless you got an oil spill. Okay? So but fluid in fluid does count, okay? Some fluids are very viscous, some are not, okay? Water's not. Oil can be, okay? All right. Okay, and there's your curve I was talking about. Notice right here, this is without air resistance. That's what we've been looking at. Now we're looking at with air resistance. Notice that's an exponential relationship, okay? That ought to tell you right out of the gate, that's exponential. All right, looking at that graph, okay? All right. Now, what about circular motion? Well, y'all, this is really kind of rerun of last chapter, was it chapter 3 when we talked about centripetal acceleration? All right, look at that right there. What is that right there? That is centripetal acceleration, isn't it? Or radial, all right? That's what? V squared over R, isn't it? What's another way I can write centripetal acceleration? 4 pi squared R over T. Is that right? Is that right? Okay? Yeah. All right, so let's come in here now and let's add mass. And what do we get? We get centripetal force. They say force net, it's actually centripetal force. mv squared over R, or what would it be using this equation? Well, it'd just be mass times all that, wouldn't it? Would it be the mass times 4 pi squared R over, oh, I forgot something, y'all. Y'all should have called me on it. T squared, yeah. Yeah? And look, we can actually do this. We can actually do this, and probably should, just to keep everything straight mathematically. Let's put it right there. Can we do that? Okay. So we could find centripetal force using this equation. Just multiply the centripetal acceleration times the mass. Okay. Because look, y'all, this is still this right here. And so is, yeah, that's still Newton's second law. Okay? It's still the same law, except instead of linear motion, it's circular motion. And it doesn't matter whether it's going vertically or horizontally or at an angle. Needless to say, if it was at an angle, we would have to throw what in the mix? Sine, cosine? Yeah. So you just do the angle, sine, cosine of the angles, right? For x and y, right? If it was at an angle, if it was moving in a circle at an angle. Okay? Okay. All right. That's all you'd have to do. Okay? All right. Now, notice I kept this slide for this reason. We talk a lot about, you hear people say centrifugal force. Well, really and truly, if you, in an inertial reference frame, there's no such thing as centrifugal force. Okay? There's really no such thing. That right there is wrong. No. Okay? Because we know that if the rope breaks, the object's not going to go that way, is it? Which way is it going to go? Direction of its velocity. And that's because of what law? Newton's what? First law, inertia. It has to. An object moving at a speed will remain in that direction unless acted upon by an outside force. Well, when the rope breaks, the outside force is gone. So whatever direction the velocity is headed, the object will head. So see, it won't go that way. It can't go that way. All right? Okay? And you say, well, what makes the water, if you punch a hole in the bottom of the bucket, what makes the water come out? Well, again, is that not centrifugal force? No, not really. It's inertia. Okay? Okay. So we use that term. We have centrifuges in chemistry. Okay. But in reality, it's just not, it doesn't exist, okay? All right. And again, this is just showing you a car on a banked curve. We know that the acceleration is going to be, since it's at an angle, is going to be towards the center, but it's at an angle. Notice you've got components here you have to calculate. Okay? So you got the weight of the car, and then you have the force in the x direction and the force in the y direction. Okay? And you find the components. All right? Now, fundamental forces of nature. And again, if you've had physics, you've heard this before. If you haven't, this is going to be new to you. But for all intents and purposes, physicists have basically summed up our forces of nature into 4 different categories. Now, the hope is that they can show, and there are researchers trying to find a connection today. Probably MIT, probably Princeton, probably Oxford, I'm sure, major Caltech. I'm sure there's research going on all around the world trying to find a connection to all the forces. In other words, they're all connected. And we just write one force. Boom. Okay? Well, we actually used to have 5. They've combined, I'm trying to remember, I think it was, I can't remember exactly what it was. It's been so long now that they combined to make electromagnetic interactions. So we have been able to combine a couple of the forces into one. But gravity, y'all, is we can see, now look right here, we can actually see some connections with these right here. There are some connections with these. They're all very related. But that one right there is the pain. Okay? That one right there is the pain. Because what do we know about electrostatic forces? Do opposite charges attract? Do opposite magnetic fields attract? Like a North Pole and a South Pole, do they attract to each other? Yeah. But do they also repel? If you take a north and a north, they'll do what? They'll repel. Well, what does gravity always do? Does it repel? No. It attracts. It always attracts. There's no repulsion with gravity. Gravity doesn't repel. It attracts. And that's the kicker. That's what the physicists just keep wanting to pull her because they think they get it, and they think, well, no, it's still because it's attractive force. It's not a repulsive force. All of these interactions here, electromagnetic interactions, like charges repel, unlike charges attract, okay? Same thing here in the nucleus. You actually have forces of repulsion and attraction. Weak interaction, same thing, okay? So those are somewhat related, a lot more related than gravity. Gravity is kind of its own thing, okay? Its own. Of course, there are physicists out there now saying that Newton was wrong about gravity, okay? They're saying that he was wrong about gravity, all right, in the universe, okay, in the universe. I'm not talking about on Earth. Sorry about that, okay? All right, and so we know what gravitational attractions are. Electromagnetic, I just told you, we have like charges. I'm just going to say this, and we'll study this next semester. The law of charges, you know what that is, don't you? I just said it. Like charges repel, like charges repel, unlike attract. Law of charges, okay. Strong interaction, this is what holds the nucleus together. Okay? And this is what results in radioactive decay. In particular, this is how we explain beta decay. Okay? Oh, good Lord. Radioactive isotopes. Of isotopes. Why did I do that? Okay? This is how we explain radioactive isotopes. In particular, how we explain beta decay. Okay? And believe it or not, and we'll study that, well, we won't really get a chance to get into radiation, doggone it, and that's one of my favorite areas of that part of physics. You have a beta particle, but you also have a positive beta particle. You have what's called a positron. Okay? And typically we write it this way. I'm old school. I like my Greek letters. There's a positive electron? Yep. It's a beta particle. What's called a positron. Okay. All right. That's supposed to be negative, by the way. All right. Okay. And that's your 4 fundamental forces of nature in a nutshell. All right? Any questions? Okay. Yeah, radiation physics is really interesting.